So, our final keynote presentation of the evening is going to be Mike Harrison. If you don't know, Mike runs a YouTube channel called Mike's Electric Stuff, which is just fantastic. Very popular with people that are working on hardware, watching Mike tear down things like X-ray machines and pill cameras and all that crazy stuff. And somehow, that sounds cool enough, somehow it seems like the stuff he's doing for his day job as well, even cooler, just huge installations, LEDs all over the place, flying over London and all that kind of crazy stuff. Really great stuff, and this presentation won't be about that, but Mike has great pictures that he can show you as well. This presentation is going to be about a Relic projector, and I am super excited to hear about this. Crazy technology, crazy amounts of money that went into the development of this thing, and I think it's going to go really deep into the details about how this thing worked and how it might apply to your stuff. So please welcome Mike Harrison to the stage.
So back, forwards, and that laser. So I need to flip back and forwards a bit on this. Is that infrared or radio? Infrared, isn't it? It's radio. Hello, Hackaday. When I'm not busy tearing things apart making YouTube videos, one of my fascinations is with old technology, specifically technology which tackled difficult problems way before we had the sort of the technology that we now understand today. So, how they did difficult things without ICs, computers, whatever. Even better if that technology is just bordering on the impractical, ridiculous, absurd, or just, stupidly expensive, whatever. And also, the common factor tends to be that at some point, new technology completely replaced it, rendered it entirely useless. So this really falls into this category very nicely. So how I found out about this, I was listening to a radio show where they do like various random queries, and someone phoned in saying that in the UK in the 1970s, they showed live boxing matches in cinemas. So the question is, well, how did they do that? It's the average person on the street wouldn't be interested, but someone like me thinks, well, how did they do big cinema screen live projections in those days? And a few people phoned in, and this specific technology was mentioned. I'd started having a look on the internet, and there is some information on the net, but there's not a huge amount. You can just about get the basic principles and a few odds and ends. I did quite a lot more hunting, and I've tracked down like a book that was written by the manufacturers of it and a few other things. So basically, this is really just the results of that research, various random bits of information I found in random places, which I found interesting. So I've tried to sort of put this together in a vaguely coherent sort of sequence to try and explain how it works and show some interesting pictures. So I'd say some interesting pictures, say 1962 live footage of John Glenn in orbit. NASA mission control now. Some of the NASA displays are like this one here, for example, showing the like the orbits and so on. Those are basically just simple mechanical projections. But you see, we actually have these video. Is this laser working? Yeah. We actually have these big screen video projections. Say 1969 live big screen video projection. That's an interesting one that I just found at random. I thought quite amusing. And obviously, live music, there's also a few large sports stadiums that installed these systems, but they were hugely expensive, as we'll see, so they weren't that common. And the other thing, not many people know about this tech because it was very expensive. It was very, if you were outside of the commercial, video projection industry, you'd have never heard of it. It's very, very obscure. So how did they do it? Now, first I'm just going to go to a little aside. Most of you, well, certainly the slightly older ones of you, will remember CRT-based video projectors. These are quite commonly seen in pubs and bars for showing sports on. Screens certainly no bigger than this screen we've got here. And there were one or two that sort of pushed the boundaries a little bit. This is the biggest one that I found from 1969 from Philips. As you can see, it's a massive piece of kit. And this really pushed the boundaries. It used CRTs with some very sort of complex optics. And of course, you have the issue of aligning all these, making sure the picture's lined up. And the performance of this, is pretty poor. 40:1 contrast. The luminous, the brightness is about the 10th of a modern LED TV. They quote a maximum of 4 by 3 meter screen, and that would have been in a completely dark cinema type environment. and say there's some nasty tech thing, like for example, this actually needed 50,000 volts on the anode to get it to work, which there's a few other issues with that. Yeah, I just found this. This is just, I love this picture. But they were obviously pushing this technology for the home use as well. But it's just a classic 70s picture. This is 1975. These are some of the tubes that they used. I say this technology was around, for example, this one here. It actually describes the tube as a kinescope. So it's a very old term. So this is probably, World War II era, using sort of funky oil-filled lenses for the optics. And one interesting point on this tube here, you can see this big glass element. This is basically because these use such a high anode voltage. That glass tube there was purely to stop the thing arcing over. So these things were running on 20, 30, 40,000 volts final anode voltage. So, CRTs, you can only really get so far with the CRT. There's some really fundamental physics brick walls you hit. Just the amount of light you can get out of the CRT phosphor, you get burn-in issues, and if anyone's seen any things like old tube oscilloscopes with black lines where people have turned the trace up too bright. Some of them, I actually found the data sheet of the tube from that Philips projector, and they actually say in the data sheet, firstly, you must fan cool the faceplate. You must make sure if the scan goes, it cuts the beam off instantly, otherwise it will just destroy the tube almost instantaneously. So, it's really running at the edge of what's possible, and because of the 50,000 volt anode potential, it actually needs a millimetre of lead shielding because of the X-rays that those high voltages can produce, and the actual tubes themselves were made using a lead glass. So, CRT. So, this is basically what they used when they couldn't do it with the CRT. Its development started just before the Second World War. It was really the brainchild of this guy, who unfortunately died sort of fairly early on in the process, but it was continued by the company that he worked for. So this is how it works. Now, I'm going to flip back and forth to this slide, because I've got a few things later on that shows some details, but this is the only really good picture I could find that actually gives a good overview. And the fundamental principle is based on what's called Schlieren optical system. Now, I've got a feeling, I think the geometry of this picture is actually wrong, because I can't actually see how this could completely work. But the basic principle is you have a parabolic mirror, and this is set up with a slotted mirror at its focal point. Light is basically coming from that mirror. So at the mirror, you basically have an image of these bright light slots where the light's coming through. The mirror then focuses that image back onto the mirror with a very slight offset, so that the image of the bright slot is focused onto the bar, such that when everything is perfectly lined up, no light passes through, because the light's coming in, bouncing off the mirror, but instead of going back through the slots, it's getting blocked by the gap between the slots. So the thing to remember is, when this is all perfectly lined up in a static condition, no light comes through. However, because that's reliant on this precise optical setup, any disturbance of the shape of the curve of that mirror means the light will go through. And that's how this system works. Because on this mirror, we have a very thin oil film. It's about 2 microns thick. So the idea is that when that oil film is completely flat, it has pretty much no effect. The light bounces off the mirror. But if that oil film is disturbed, that produces enough distortion of the geometry of the mirror to allow light to pass back through those slots. And the way that disturbance was created was by scanning an electron beam over it. So the electrostatic field on the surface of that mirror produces local variations in the surface of that oil. So obviously the electron beam scanning, that's how the video scan is created. You modulate the electron beam to modulate the brightness. So, it's a sort of simple-ish principle, but the actual practicalities are what made it, borderline impossible and impractical. So if we actually have a look at what's happening on the oil film itself, so we have this surface with, this would be the equivalent of black, no image. And for a full white, we have this sort of little wavy lines at about a 2 micron depth, which are caused by the electrical charge. So you've effectively got electrostatic charges repelling each other on the surface of the film, which causes the surface distortion. I've got a few slides on that later. So, for example, here there's an example of, say, alternate black and white stripe. So we've got alternately a rough surface, a smooth surface to provide that virtual image. Now, even just creating this is insanely complicated. We have two effects going on here. As the electron beam sweeps across, as the electron beam is basically pointing at the film, the charge gradually builds up over time with a certain time constant. And then when the electron beam goes away again, it discharges itself again with a certain time constant. So there's a lot of optimization required such that you balance out these times so that over a period of a frame, you don't get too much blur from one frame to the next, and it reacts in a sensible amount of time. So obviously it's hugely dependent on the characteristics of the oil, the characteristics of the beam, and all sorts of things. One issue which I totally understand the exact reason for, but I believe it's the obvious way to modulate an electron beam is to do what they do in a cathode ray tube, is adjust the beam current. Now, I think the problem with that is that a higher beam current, the more energetic electrons will actually bury themselves deeper into the film. So you don't get anything like a linear. What you're trying to create here is a surface effect. So if your electrons are going so fast they go through the film, it's not really going to do anything for you. So instead of modulating the beam current, they actually modulate the beam velocity. So they scan across the surface, but slow down and speed up to deposit the amount of charge they require to generate the amount of intensity they want for that spot. Later systems, they also had a system where they could actually modulate the size of the spot as well, but it was always at a constant beam current. And so as far as I can tell, that's purely to make sure that it maximizes the effect on the surface of the oil, because anything else is just going to really, mess things up. Now, if we go back to this other thing, one issue is that over time you will get a charge gradually building up, because the oil is basically an insulator, so the charge will build up on the surface. So the next of many complications on this system is what they have to do is the mirror actually rotates continuously, fairly slowly. It's not like spinning like at scan rate. It's just a slow, again, I'm not sure exactly what speed, but it's like a fairly slow rotation. And then you have this wiper here. So this creates a nice smooth, it wipes the oil into a nice smooth surface as it rotates. Right. Now, the oil film thing is ridiculous. I found this fantastic paper. This was from 1947. It's 40 pages of this stuff. So it's combining the electron physics, the fluid dynamics, the electrostatics, the phase of the moon, God knows what else. And there are 180 equations in this paper. So by all means, study it if you understand these things. But for example, this one here is showing the various effects of the depths, different electron energies and so on, and field strengths. I'll just take some random sort of formula porn to show here, but it's, just that sole aspect of the system is complicated, and then there's a whole load of more stuff as well. So we've got a vast number of challenges. Because we're using electron beams, the whole thing's got to be in a vacuum. Because we've got oil, that oil will continuously be evaporating off, so we have to continuously pump. It's not like a CRT where we pump it down and seal it. This thing is continuously being pumped down by a vacuum pump. As I mentioned before, and say it takes a few hours to pump it down if you just start it up from cold. I think they normally actually kept them pumped down wherever possible, but several hours to pump it down to a sufficient vacuum to start the thing up. So they use this velocity modulation to get the effect they want on the oil surface. Now, of course, all this stuff has to be done really accurately, because your image on the oil film is about 75 millimeters wide, about 3 inches. But obviously, you're projecting that onto a huge screen, so the tiniest bit of vibration is going to affect the image. And of course, because it's an oil film, you might get the motion on the surface. So this thing has to be made to high precision, so it's big and heavy. Another complication. Whoops, sorry, wrong button. You can't. Traditional CRTs use an oxide-coated filament, which means they emit electrons at a relatively low temperature, like a low red heat. If you look at any really, really old valves, particularly transmitting valves, you'll see they almost look like light bulbs because they use a raw tungsten filament. And that was necessary just to get emission, and the oxide filament was a later development. But unfortunately, because of the contamination of the oil, that meant they couldn't use the oxide-coated filament. So basically what that meant was the cathodes wore out really often. The typical lifetime was about 50 hours. Now, in later models, they did some clever tricks. They had like an internal turret, so you could instantly switch in a new filament. Because obviously, if you've got a big sports event, the last thing you want is to be able to go and replace the filament on your projector. So they've got a fast switchover system. And they also had like an airlock type system, which you'll see on the later ones, where you don't have to let the whole thing back up to air. You could just there was only a very small volume that you could seal that off, let that up to air, change the filament, and then just pump that bit down again relatively quickly. So the oil film itself, say, it has to be constant thickness. The wiper rotating mirror avoids this charge build-up thing. Things like also, one of the reasons I think why it takes so long to pump it down is that if it's been left at atmospheric pressure, you'll get oil bubbles, so you have to make sure all those oil bubbles come out, otherwise you get like a 1960s oil wheel type effect on your projector with bubbles appearing. So you've got this continuous rotation. The other thing is the characteristics of the oil are clearly very important, which means that you have to hold it at a constant temperature. Now, in the early models, this ideal temperature turned out to be 10 degrees C, so as well as your high voltage or vacuum pumps, you also need a refrigeration unit in the same case to keep the oil at the right temperature. Later on, they did get around this and they found a way of using oil at I haven't found a reference to the actual temperature. I believe it's probably in like the 40 to 50 degrees, so it's warm rather than hot. So, and obviously warming the oil is a lot easier than refrigerating it, so that made life a little bit easier. And you can see I've got quite a few pictures of the various models as they developed, and you can see how some of these improvements made it very slightly simpler. So then we have the actual optical system. Again, it has to be very precise. Originally, of course, they used carbon arc lamps, which were the same things that we used in cinema projectors. The complete end-to-end efficiency of the optics is 2%. So 98% of the light you stick in this thing just disappears as heat. So, for example, all the lenses and everything actually had to be water-cooled just purely because of the amount of energy. If you imagine you're losing 98% and you're still wanting to produce a big image, then the amount of light you're putting in is just insane. So anything that light passes through is going to get hot, so that has to be water-cooled. For the color versions, the first one they used the sequential field color, so you send like red, green, blue in sequence, and that, of course, needed special cameras because you couldn't have like an electronic scan converter that you'd have nowadays. And again, still more challenges. Electromechanics, of course, it's all analog. We're talking 1940s, 1950s. 200 valves or tubes for those the other side of the Atlantic. You've got the high voltages. Because of the need for all this rigidity, it was really heavy, so this is not very portable, although apparently they did move these around cinemas for these events, but I'm sure that was an interesting operation. And obviously you've got your chiller, you've got your vacuum pump that are producing vibrations, which again, you need to keep that away from your nice precise optics in your oil film. And magnetic field from your motors. You've got this electron beam scanning. Any magnetic field would distort that, so again, that's something you need to take care of. So, this is one of those technologies which is borderline impractical, and certainly when they were starting up, they probably didn't really know, if it was even possible. So this is one of my favourite pictures. It just looks so amazing. Hello, what happened? Hello. Thank you. I think this projector's getting jealous. We've got a bit of projector envy going on here. So 1947, interesting what they did here, because obviously you've got this massive great arc lamp. It's not really a very nice thing to have in the lab while you're working on the other stuff. So they actually split these over 2 floors of the building. So they stuck this arc lamp. I think they had that upstairs out the way, cooled off, and then they had all the projector stuff downstairs so they could actually work on it. So again, they progressively developed it. This arc lamp, I think this is actually just a standard one that was used commonly for cinema projectors. It looks very much the same thing you see on old projectors. This was one of the first colour ones where they had a colour wheel. Again, it was probably the height of the technology for carbon arc lamps here. 375,000 lumens on the arc lamp. It also fed the carbon rods onto a rotating disc, so it would actually run continuously for 8 hours. And a lot of this tech was developed really for film and cinema applications at the time. So here we're just coming to the point where they were getting it into a form where it was nearly ready for production, and this nicely coincided with the development of xenon arc lamps. So you see on this, basically the last pre-production on the left, we've still got this arc lamp on the top, but that was then replaced by a xenon arc lamp that just came along just in time. So 1958 was the first production units. And you can see out the front here, we've got, this is the lens here, then this is the electron gun, and then we see this is the sort of the airlock part. So there was some way, again, I haven't found any detailed images of exactly how this worked, but I think the idea was that in here, I don't know where they had the filament turret at this stage, but the idea was that this is how you got at it to replace the filament. Obviously, you don't, something that needs doing every 50 hours, so you need nice access for that. I believe that in addition to the electronics here, I think there may have been an additional rack as well, full of other electronics. Again, all full of lots of valves. So here we're getting, went into the production. It's sort of quite condensed and compact. We've got all the electronics in the back here. I think this is still a valve, 1960, so this is probably still valves. 500 lumens, so we're getting to sort of similar sort of intensity as low-end projectors these days. In the bottom here, we can see this is the chiller unit. Next to it, we've got the vacuum pump. We've got all these tubes. Some of this piping would be, for example, for the water-cooled optics. And the light comes down in the top there, and this is the whole sort of big vacuum chamber that's got all the goodies, and I think the mirror actually sits at the bottom here, because obviously you want the mirror to be vertical because you've got this oil film and you don't want the oil to run around. So this is the point where they figured out they could do without the refrigerated oil, so basically the main difference here is the fridge unit's gone, the rest of it all looks fairly similar. They seem to be slightly less stuff in the back. In 1965, maybe they were starting to transistorize it. But this was just a fairly sort of minor development of it. Stepping back a little bit in time, this was the first simultaneous color unit, which was basically three units in one box. Again, this is an early prototype on the left, which is huge, and then that gradually got down to a more sensible size. So we've got the main unit here, and I think they moved all the electronics out into this one or two separate racks. And there was also like this remote control panel and so on. So 1970, it's transistorized, it's much slimmer. We've got just a relatively more sensible size rack. You can see, get an idea of the scale from the right-hand side. So we're getting down to a scale similar to a cinema projector. These were fairly practical, decent brightness. So these were, despite the ridiculousness of the tech, it had become a very, usable system, very expensive, but it worked, and apparently the performance was actually very good in terms of image quality, brightness, and indeed reliability. Once they got this down, they were surprisingly reliable. And this was pretty much the end of the development. Multi-standard, I think this one does HD. It's actually, I think maybe this may be multi-standard PAL NTSC for US and Europe. There was an HD version after this. I think that this is in a museum somewhere. I don't know where. If somebody knows, please tell me, because I'd like to go and actually see it. I don't know if it's still on display. But you see, we've got the Edwards vacuum pump down there. And again, you can just about see, I'm not quite sure what that is down there, but so we've got three lenses, and again, we've got these easily accessible cathodes. And these were sold by a company called Gretag, who are still going. They're not in this business anymore. But basically, they owned this market from when the unit was launched right up until, the late 80s, early 90s, when LCD and DLP type projectors, they were pretty much the only game in town. They had the entire market for a huge amount of time, which is it's actually not untypical of this sort of ridiculous technology. One of the other technologies that comes to mind is the Linotype typesetter, where one company just had this amazing, ridiculous machine, but it did the job, and they just owned the market, and then the whole thing just went almost overnight when technology replaced it. So here are the screens. This is the setup they had at NASA. So we've got the projectors, the IDA4. Sorry, did I mention it was called the IDA4? I can't remember if I mentioned that or not. So we've got the projectors down here, and we've got two mirrors here to shine on the screens just to shorten the projection path. So these were the screens you saw right up at the top at NASA. Just a few random bits of information I found. 650 was their entire lifetime production. So the last version, the HD version, 1988, but obviously, that got fairly quickly replaced by more modern technologies. So until the 1990s, it was the brightest video projector available anywhere. Discontinued. The last one I found any information about was in year 2000, still going. And obviously it was stupidly expensive. A colour system in 1970s, £250,000, which is about 2 million-ish. So, only the very, huge sports stadiums. I think there may be one or two rental companies, but massive investment. Just a few other rounds, say, 4-projector installation, I think a US sports stadium, $2.8 million. In 1991, they were maybe regretting that a little bit, perhaps. I'm not sure how long that lasted for. NASA had 34 of them at the height of the Apollo program, so they were obviously a very major customer. Of course, they had the budget. So, and say the cathodes, that was the main consumable, 50 to 100 hours. Cathodes cost $200, the xenon bulbs $5,000. But even just to have one of these sitting in a warehouse was expensive because you had to regularly pump them down. If you just left them up to atmosphere, what happened was that the oil got contaminated and you had to strip the thing down and clean it out. So, even having this sitting there doing nothing was actually costing you money. But yeah, amazing reliable. 50,000, apart from the routine replacements, an average life of 50,000 hours without repair, which, considering how complicated it is, it's pretty amazing. But developed over 20 years, so they obviously put a lot of work into it. And obviously, if you own a piece of kit that expensive, you're going to get it regularly serviced and looked after. You're not going to mess about. The only competition was a device called a Talaria from General Electric in the USA. Now, I've found very little technical information. It's broadly the same principle in that you've got instead of the parabolic mirror, they used a glass disc here, which rotated. They used like an external coiled as a motor. But unusually, this was a sealed system, so I don't know how they dealt with the issue about the cathode contamination, but it was the idea was it was sealed. I suspect they maybe had a system where they could refurbish and open these up and refurbish them, but I think the basic idea was it had a fairly long lifetime. Now, this used some very, very complex optics, which I don't pretend to understand, to actually use a single device to do color. And this was they had some very strange way of segregating some of the primary colors by polarization, by mechanical separation. And from the reports I've seen, it sort of worked, but it looked pretty rubbish. It was color, but it was probably more of a technical achievement in terms of being able to do it at all than actually a practical idea. So I did find a picture of the tube. You can see some of this funky optical stuff going on here. So we've got the glass disc here, the electron gun down here. So it looks like this can be separated. It looks like some sort of sealing flange back there. I did actually find one of these on eBay in the US. If it was in the UK, I would have bought one for the hell of it. This was the single tube color version on the left. Originally about $100,000 US, $200 an hour running cost, which I think was mostly the lamp. It may also have been like a regular replacement of the valve unit. I don't know what the service interval of that. So these are probably sufficiently recent. I'm sure there will be some manuals for these on somebody's shelves. I would love to have a manual for one of these. If anyone sees one, please let me know. And they also did triple for proper color. They had these three stack projectors, and again, I've not really found much information about these. So that was really the only competition they had until LCD and DLP projectors came along. There's two really good books. The first one, most of the information actually came out. This was actually a book produced by Gretag, who manufactured them. So this has got a lot of historical information, not too much technical stuff. There's another book here which is in German, which has got some bits of information. But I did this presentation a few years ago in London, and there was actually a German guy in the audience who was really keen, so I sold him my copy of that book because it wasn't any use to me because I couldn't read it. These are pretty much the only. There are one or two papers in a few industry journals which I've found one or two, but other ones are behind paywalls. But I'm not sure there's actually a great deal of more information in those documents. So, of course, now we have DLP projectors that are just, again, they totally own the whole industry. Every single big screen cinema projector uses a DLP from Texas Instruments. If you want to see actually what's inside one of these, I took one apart, of course. Again, when it was new, it was like the top end, small-scale cinema projector. But the lamps cost £1,000, so I thought I probably didn't really want to fix that. So if you want to see what's inside one of those and all the optics, you can go and look at that. So, yeah, the IDA 4. Thank you. Oh,